Section 2.1 Part B is called the addition property of equality. Watch what happens when I take something that's clearly true and add the same quantity to both sides. 3 plus 2 is 5. 3 plus 2 is 5. Obviously, if I start with something that's true and add the same amount to both sides, the resulting sentence should also be true. What if I start with a sentence that says x equals x? This may not be as obvious, but if I've selected the letter x to represent a value I don't know, then x has to equal that value, regardless of where it appears or what side of the equation it's on. So this is always true even though we don't know what x is. Now, if I add 2 to both sides, I'm getting the same result as I did before. If x equals x, then x plus 2 must equal x plus 2. That seems obvious enough, right? Okay, what if I start with a sentence like this? X equals 3. If x equals 3 is a true statement, then x plus 2 must equal 3 plus 2. In other words, x plus 2 has to equal 5 if we start out with x equals 3. This is going to come in handy because the two sides of my equation can look different, but I can use this property to solve the equation. For example, what if my equation said x minus 2 equals 4? Well, I hope you can see in this simple example that the number x is going to have to turn out to be is probably 6, because the only number I can subtract 2 from and end up with 4 is 6. But what if the question wasn't so straightforward? We need a strategy for solving equations more complex than this. Let's try it out on this simple equation, and then we'll be able to apply it later to more complicated ones. Let me start by moving this over a little bit to give us some space. Now, I have said that I can add the same amount to both sides of the equation, and if this is true, then the resulting equation will also be true. What should I add? Well, I can add anything I like. I can add 7 to both sides, and that'll give me another new true statement. X plus 5 equals 11. But it hasn't really helped us very much. So we're going to choose a value to add here, and of course here. That actually helps us figure out what x is when it's completely by itself. What value could I add to this side of the equation that would get the x alone? In other words, that would get rid of this minus 2. Well, if I subtract 2 and then add 2 from x, then I'm adding 0. So I kind of want to make this plus 0. The thing is, if I add 2 to this side of the equation, to keep the statement true, I also must add 2 to this side of the equation. When I simplify this, I get x minus 2 plus 2 by combining like terms, and that's 0, equals 4 plus 2, which is 6. X plus 0 is x. So x equals 6. The solution to the original equation is 6. How do you know for sure that the work you've done is correct? Well, what I have here is a potential solution for my original equation. Let's rewrite the equation, x minus 2 equals 4, and then rewrite it again with a blank space for the number we're going to test, just like we did in Part A of this section. I'm checking to see whether 6 is a solution to this equation. What's 6 minus 2? It's 4. Does 4 equal 4? It does. So that means that 6 is a solution to this equation. And in fact, the 6 came from the work that we did on this side. That means that the solution that we found was the correct one. The work we did was correct. Okay, let's do another couple of examples. What if I had x plus 6 equals 5? Again, I'm going to move over the equals 5 just to give us a little bit more room. What number can I add to both sides of this equation so that when I'm done, x is all by itself? Since x has 6 added to it, let's add -6. If I do it to one side, I have to do the same thing to the other side. I've chosen to add -6 because 6 plus -6 is 0. That lets me rewrite the left-hand side of my equation as x plus 0 and the right-hand side as -1. X plus 0 is of course just x, so x equals -1. Again, I've taken a lot of steps here that you may not need to write out. Let me show you what I mean. Instead of adding -6 to both sides, you can think subtract 6. Because plus 6 minus 6 is 0. And then it seems pretty obvious to me that x plus 6 minus 6 is x plus 0. And I know that x plus 0 is just x. So I might be able to jump straight from here to here. I do need to show the -6 I've written on both sides. In order to get credit for this problem, I need to show what I did to both sides of the equation to get the answer that I did. Let's check our answer. We started with x plus 6 equals 5. If we rewrite the equation x plus 6 equals 5 with a blank space for the x, and then substitute the value we found for x, what happens? -1 plus 6 is 5, and 5 equals 5. So the solution that we found is the correct one. The answer is x equals -1. Here's that equation again. And here it is before I move the 5 over. I want to show you another common way of indicating what it is you're going to do to both sides of your equation. What I've decided I need to do is add -6 or subtract 6. I have to do it on both sides. So instead of writing it alongside, I might write it underneath. Let me make an observation here. When I say both sides, especially when I'm writing my work this way, what I mean is both sides of the equal sign. I have to subtract 6 from both sides. On the left-hand side, x plus 6 minus 6 is now just x. In other words, the plus 6 that I started with and the minus 6 that I wrote cancel each other out. Or x plus 6 minus 6 is like saying x plus 0. On the right-hand side of the equal sign, I have 5 minus 6, which I know to be -1. X plus 0 is just x, and x is equal to -1. That's the same answer as I got before. I really don't mind which technique you use, writing your -6 alongside or underneath. You just need to be really careful that you're adding or subtracting from each side. The rule, if you choose to add or subtract from an equation in order to isolate x, is that you have to do it to both sides. Here's another example. A plus 3/4 equals -1/2. I can either move my -1/2 over to the right and then add or subtract to both sides. What value do I want to add or subtract? Well, if I want to find the value of a, I need to figure out how to get rid of this thing that's stuck to a. In other words, 3/4 more than a is -1/2, but what is a? Well, if 3/4 more than a is -1/2, then 3/4 less than that quantity will be my value for a. So I'm going to subtract 3/4 from both sides. A plus 3/4 minus 3/4 is a plus 0, or just a. In other words, you don't have to write this step this way. The right-hand side of my equation now says -1/2 minus 3/4. I need to do some scratch work here. -1/2 minus 3/4 is an addition or subtraction of fractions. My lowest common denominator is 4. This fraction already has a denominator of 4. This one would need to be multiplied by 2 on the denominator to get a denominator of 4. Multiplying the numerator by 2 gives me 2. -2 of something minus another 3 of the same thing is -5 of those. -2/4 minus another 3/4 is -5/4, or -5/4. This arithmetic, -1/2 minus 3/4, gives me this number, so I can replace the right-hand side with -5/4. A plus 0 equals -5/4 means a equals -5/4. It's quite likely I won't bother writing this anymore. As you can see, the only change from this line down to this one is I've eliminated the plus 0. We know this is going to be 0. That's why we chose to subtract 3/4. We wanted it to be 0. Here's the same equation, and here it is before I move the 1/2 over. Subtracting 3/4 from both sides of the equation can also be written this way. Subtract 3/4 from the left-hand side, and also subtract 3/4 from the right-hand side. The right-hand side of what? Well, the right-hand side of the equal sign. You don't need to draw an arrow here. I'll continue to do this for a while, and then eventually that will drop. All I'm doing here is helping you to visualize that the -3/4 is being written once on each side of the equal sign. Now let's do our arithmetic. Can you see that 3/4 and -3/4 are similar terms? A plus 3/4 minus 3/4 is a plus 0, but that's just a. -1/2 minus 3/4 is -5/4. We did this arithmetic already in the previous version of this question. This is my final answer. Okay, that last one had a fraction in it. Here's one with a decimal. 7.3 plus t equals -2.4. Another thing to notice about this problem that's a little different from some of the other ones that we've done is that the t is in the second position. But that doesn't matter. Here's a number. I'm going to add another number, and that equals a number. The fact that the t is in the second position is coincidental. Another observation to make is that, although it doesn't say so explicitly, 7.3 is positive. There's no sign in front of it, and when that's the case, we assume the number is positive. In other words, it's got an invisible positive in front of it. So if I want to isolate the t here, get it by itself so that I can find out what its value is, the thing I need to get rid of in this case is the 7.3. What can I do to the left-hand side to get rid of 7.3? Subtract 7.3. But if I do that, I must do it once on each side. Now, 7.3 minus 7.3 is 0. These are similar terms, so I can add them together, and when I do, I get 0. 0 plus t is just t. This arithmetic, a negative number minus a number, is the same as a negative number plus another negative number. So my result here is going to be a larger negative number. Negative 2.4 minus 7.3 is negative 9.7. This is my answer. Let's check it this time to make sure it's really right. My original equation said 7.3 plus t equals negative 2.4. If t really is negative 9.7, then this will be a true statement. What's 7.3 plus negative 9.7? It's negative 2.4. Since both sides of the equation are equal, the value I found for t is the right one. It's the solution to the equation. So my answer is t equals negative 9.7. Okay, here's another one. Negative x plus 2 plus 2x equals 7 plus 5. In this case, I can't figure out what x is because I have two x's on the left-hand side of the equation. I can't isolate it. What I can do is simplify both sides of my equation first. So I'll need to call on the skills I learned in Chapter 1. Reversing the order of these two terms, I get negative x plus 2x plus 2 equals 7 plus 5. This is the commutative property of addition. Now I can combine similar terms. If I owe somebody 1x and I find 2 x's in my wallet, I'll pay the debt and still have 1x left. I can also combine the similar terms on the right-hand side. Now, I don't need to write 1x, I can just have x. Now my equation is in a form I'm familiar with, and I know that in order to isolate the x and get it completely by itself, all I need to do is either add or subtract the value that's stuck to the x to get rid of it on the side where it's in the way. Here it's in the way. If I subtract 2, these add up to 0. The left-hand side now is x plus 0, or just x. The right-hand side, simple arithmetic tells me, is 10. And there's my solution, x equals 10. Let's check it. Here's my original equation with the x's removed and replaced with empty parentheses. I'm claiming now that x is equal to 10. So let's check and see if that is in fact the solution to the equation. There's my invisible 1, and so this is a multiplication problem. This is multiplication also, so I'll do those first. Negative 1 times 10 is negative 10, plus 2 so I don't forget it, plus 2 times 10 is 20. And that should equal 7 plus 5. Now that it's all numbers, negative 10 plus 2 is negative 8. 7 plus 5 is 12. Negative 8 plus 20 is 12. The answer I found, x equals 10, works, so it is the right answer. Another example, 4 times 2b minus 3 minus 7b equals 2 minus 5. What value does b have to be here to make this sentence true? It's not obvious, is it? We need to use distribution, the commutative property of addition, and combining similar terms to get this problem ready. We'll start with the distribution. 4 times 2b and 4 times negative 3 minus 7b. That's my left-hand side, rewritten with the 4 distributed across the sum. I haven't forgotten to write down the minus 7b. The right-hand side of the equation is 2 minus 5. I could use the associative property here to rewrite this piece. In fact, that's what I'm going to be doing, but I'm not going to rewrite it. I'm just going to think 4 times 2 times b is 8b, plus 4 times negative 3 is negative 12, minus 7b so I don't forget, equals 2 minus 5. So I've done all my multiplication. Let's go back and change this plus a negative to minus 12. Now I can use the commutative property of addition to reverse the order of these terms. Or I can just think, look, here I have 8 b's. Over here I'm going to spend 7 b's. If I have 8 of something and I spend 7 of them, then I only have 1 left. I have 1 b. But I haven't done anything with this, so let's write it down and copy out the rest of the problem. I don't need 1 in front of the b. At this point, I could add 12 to both sides. It wouldn't be wrong, but what I'd like to do first is to simplify the rest of the equation as much as I can. 2 minus 5 is negative 3. I've run out of room here, so I'm going to rewrite the problem up here. I'm not changing anything, I'm just copying it down as I have it in that last line. Now the problem is in a form that I recognize as being ready to add or subtract from both sides. I'm trying to figure out what the value of b is. At this point, I know what b minus 12 is, but that's not really helpful. If I add 12 to both sides of the equal sign, then on the right-hand side, I'll get negative 3 plus 12, which is 9. On the left-hand side, I get b minus 12 plus 12, which is 0. And of course, I don't need to write the plus 0. My answer? B equals 9. Okay, last one for this section. 3x minus 5 equals 2x plus 7. When I write an equation, what I'm saying is this side has the same value as this side. It's kind of like saying they weigh the same thing. If they weigh the same amount, then it's kind of like saying if I put each quantity on one side of a balance scale, the scale will stay balanced. There we have it. 3x minus 5 has the same weight as 2x plus 7. So I basically have 3 x's on one side of my scale and 2 x's on the other side of my scale. What happens if I reach over and pick up these 2 x's and take them off the scale? The scale's going to tip, isn't it? But if at the same time I reach over and I pick up 2 x's from this side of the scale, then the scale will stay balanced. Let's do that now. Let's take 2 x's off each side of this scale. There we go. 2 x's from this side means I don't have any x's left at all. Taking 2 x's off this side means that out of the 3 I had before, I only have 1 left. Now I essentially have an equation that says x minus 5 equals 7. If we do the same thing algebraically, we say minus 2x on this side and minus 2x on this side gives me a different but equally valid, equally true statement. 3x minus 2x is 1x. But I still have minus 5, so I'll write that down so I don't forget to work with it. My equal sign goes there. 2 x's take away 2 x's is 0 x's plus 7. As before, we don't need to write 0x. That's just 0. 0 plus 7 is 7. So x minus 5 equals 7. But that hasn't completely isolated x. This question has a second step. Now that I only have 1x, I can add 5 to both sides, like I did in the previous examples. Adding 5 to both sides gives me a left-hand side that says x minus 5 plus 5. Well, minus 5 plus 5 is 0, so all I've got left there is x. On the right-hand side, 7 plus 5 is 12. So my answer is 12. Let's check our answer to make sure it's right. My original equation was 3x minus 5 equals 2x plus 7. Rewriting that with empty parentheses gives me this. And then I can substitute the value I found for x in place of x. What I'm doing is checking to see if this is true. Multiplication before subtraction. 36 minus 5. Multiplication before addition. 24 plus 7. And again, I'm checking to see if this is true. What's 36 minus 5? It's 31. What's 24 plus 7? It's 31. So this answer is correct. It's very important to note here that I'm not saying that the answer to the problem is 31. 31 is just what I happened to get on each side when I plugged my potential answer in. The answer is still x equals 12. 12 is the number that makes this statement true when I replace x with it. I've done all of these questions without talking at all about the vocabulary of solving an equation. But that's exactly what I've done. All of the examples and all of the exercises in the textbook, in addition to the problems you'll see on WAMAP, will ask you to solve the equation. Some of them may say simplify and then solve. But solving the equation is what we've done with every single one of these. We're going to see more in the next section, and in fact throughout the rest of this chapter. Solving an equation means finding the solution to the equation. And the solution to an equation is the number that makes it true. So solving an equation is finding the value for the variable that makes the equation true.